Alright, in the first part of the Kinetics, the lesson from earlier this week, we learned about instantaneous rate. And instantaneous rate is looking at the rate of a reaction as it occurs over time. So if you look at the rate of a reaction at certain specific moments in time, you can calculate its rate at those specific moments in time looking at the change in the concentration over the change in time, which is essentially the slope of the line tangent to this curve at that specific time that you are looking for. Those of you who are in calculus have kind of dealt with some instantaneous rate things. So we can find, based on our data, we can just calculate the change in the rate over these certain periods of times that are given. So we look at the difference in the concentration over the difference in time, and that gives you your rate. And remember that when you're comparing rates of reactants to products, reactants are disappearing, so their rates are negative. Products are appearing, so their rates are positive. And there's a stoichiometric relationship between them. If you knew the rate of a reactant, you could calculate the rate of a product using their stoichiometric relationships. So instantaneous rate is the rate at a specific, over a specific period of time. And that's what this graph over here is showing us. We're looking at the instantaneous rate at different moments in time. So if we wanted to know the instantaneous rate at time equals 0, all right, then we would draw a line tangent to the curve at the curve's point of time is equal to 0. And then we could calculate the difference in the concentration over the difference in time. Same thing here. If we wanted to know the instantaneous rate at time is equal to 600 seconds, which is not a point in our data table over here, we would find where 600 seconds is right there, draw a line tangent to that curve, and calculate the difference between the concentrations and the time. And that would give you the instantaneous rate, which is essentially the slope of that line. So the change in the concentrations over the change in time. And that would give you your instantaneous rate at 600 seconds. So we've practiced a little bit with that. You guys did your homework assignments on that. Now we're going to move into the second part of kinetics, which is called the differential rate law. The differential rate law shows the relationship between the reaction rate and the concentration of reactants. So it's really, really important for you guys to latch on to this concept. The differential rate law is concentration versus time. We're dealing with concentration and we're dealing with time. So we're looking at how the rate is affected when the concentrations are changed. That's where differential rate law. The difference in the rate when you change your concentration. Now this is an example of how you write the differential rate law. The rate, which is your change in concentration over change in time, is equal to K, we'll talk about K in just a second, times the concentration of the reactants raised to M, times the concentration of the reactant 2 raised to the N, and so on and so forth for all the reactants that you have. So first we need to talk about what all these things in here are. The first thing is K, and K is called your rate constant. Now, rate constants are constants for certain reactions at certain temperatures, but is not the same little k for all reactions. Every kind of reaction has its own rate constant. Okay, notice this is little k, and little k is for rate constant. All right, so we're going to talk about k and deal with calculating k. The second thing that you'll notice in your differential rate law are these exponents. This exponent is m, this exponent is n, and You might go, well, what do those exponents mean? Well, the exponents tell us the order of the reaction with respect to each reactant. Now, when you're talking about order, what you're talking about is what happens when you change to the rate when you change the concentration. Does changing the concentration of the reactant, 1, affect the rate of your reaction? And if it does, how does it affect it? All right. So there's 3 categories of orders. The first category is a zero-order reactant. And when you change the concentration, either you increase or decrease the concentration, it has no effect on the reactant, on the rate. No effect on the rate. All right? So it doesn't matter if you double the concentration, then the rate stays the same. If you quadruple the concentration, then the rate of the reaction stays the same. There's no effect or zero effect on the rate when the concentration is changed. So that's a zero-order reaction. All right. The second kind of reactant is a first-order reactant. All right. And first-order reactants, when you change the concentration, it has what we call a direct effect on the concentration. So, if you double the concentration, then the rate is doubled. If you triple the concentration, then the rate is tripled. If you half the concentration, then the rate is halved. All right. So, first-order reactants have a direct effect on the concentration. Then the last kind of order is a second-order reactant. Second-order reactants have a really big effect on the rate. If you change the concentration, then that change has an exponential effect on the rate, which means if we double the concentration, then the rate is raised to the 4th. So it's exponential. It's basically 2 to the second order. Okay? Or if we triple the concentration, then the rate goes up by 9, which is 3 squared. Okay? If we quadruple it, then the rate would go up by 16, 4 squared, and on and on and on and on and on. All right? So the first thing that you have to learn is how to identify the orders of the reactants given data and given rate information. All right, so we're going to go to this table, this slide that explains what is called, what we'll refer to as table logic. And when we're dealing with table logic, basically what we're dealing with is a data table. We're looking at a data table, and we're looking to see how a change in the concentration affects the rate in the data table. And I'm going to walk you through a couple of practice problems so you guys can get a good idea of this. But you want to be able to identify what's happening to your reaction as you're changing your concentrations. All right, so let's look at table logic. All right, when you're using table logic, you look at 2 trials where the concentration of one of the reactants is held constant. All right, so that's the first step. You got to find 2 trials or 2 data lines where the concentration of one of the reactants is being held constant. Then you're going to look and you're going to focus on the other reactant. So ask yourself how the concentration changed for those 2 trials. Was the concentration doubled? Was it tripled? Was it halved? What did we do to the concentration of the second reactant? All right. Once you figure out what you did to the concentration of the second reactant, then you need to look at the rate and see what happened to the rate. Was the rate doubled? Was it tripled? Did anything happen to the rate? Did it go up exponentially? All right. Now, I put on here expect easy math because they're going to make it so that the math, it's really easy for you to identify what happens to the concentration and then in turn what happens to the rate. So, what you're looking for, did changing the concentration have zero effect on the rate? If it had zero effect on the rate, meaning the rate didn't change, then it's called a zero order reaction. Second, did the rate double when the concentration of the other reactant was doubled? All right, or triple, or quadruple, or whatever you did to the second reactant, did the same thing happen to the rate? If that's the case, then this is called a first order reaction. All right. And then finally, if it isn't a zero order and it isn't a first order, well then you need to check and see if it's a second order. All right. So did the rate quadruple when the concentration was doubled? Meaning whatever you did to the concentration, all right, did the square of that happen to the rate? If that's the case, then it's a second order reaction. All reactants in AP Chemistry are going to either be a zero, a first, or a second order. All right. Now, there is a third order reaction, but we don't have those very often. All right. Did the rate increase by a factor of 8? All right. When you doubled the concentration? All right. If so, that's a third order. And we don't have those very often, but I just wanted to tell you in case you run into them. All right. So once you've determined the order of the second reactant, now you have to go back and do the same thing again, but this time switch the reactants and see what happens to the second reactant when you held one constant. All right, so let me walk you through some examples so you guys can see what's going on with what we call table logic. All right, so here is our sample problem. All right, they're giving us several experiments. We've got 8 experiments here, and they're giving us the initial concentrations of our first reactant, which is ammonium, and our initial concentration of our second reactant, which is the nitrite ion. All right, and then finally over here they're giving us rates. All right, so this is rate, and these are concentrations. So if you have a data table that looks like this, you know they're asking you about the differential rate law because it's concentration and rate, and they gave you the rates. You're not calculating any rates. So here's the reaction. We've got ammonium and nitrite are reacting to produce nitrogen gas and 2 moles of water. So let's look at our data in our tables. If you'll notice right here in trials 1 through 4, then this is held constant. All right, we're going to look at trial 1 and 2 because nitrate is the same in trial 1 and 2. All right, so here's what we're going to do. If we hold this concentration the same, we're going to look at what we do to the concentration of the ammonium. So here, what did we do to the concentration of the ammonium? Well, we doubled it, right? Because it was 0.1, now it's 0.2, that's double the concentration. Then we want to go look at our rate and see what happens to our rate. Well, if you look at our rate, it was 5.4 and now it's 10.8, which means our rate doubled. Alright, so since changing our concentration or doubling our concentration did the same thing to our rate doubled, that means this reactant has an order of 1. It's a first order reactant. Alright, so NH4 has an order of 1. That's the order of the ammonium. Okay? Now, we got to find the order of the nitrite also. So we're going to go and we're going to look for trials where the nitrite, the ammonium stayed the same and the nitrite changed. Alright, and that happens in trials 5 through 8. So we can compare any of these. I'm just going to pick the first two. So these two, it's the same. Alright, and now let's look over here at what happens to my nitrite when I change the concentration. So what happened to my concentration? I doubled it. Alright, and let's look at what happened to my rate. Well, it was 10.8, and when I doubled it, it now became 21.6, which is also double. Alright, so what did I do to this? I doubled it. What happened to my rate? I doubled it. That's a direct effect, and because that's a direct effect, then we now know the order of the nitrite is also a first order reactant. And we can look at other trials and see what happens in other trials. Alright, if we compared trial 1 and trial 4, the nitrite stays the same. What happened to my ammonium? Well, it went up 6 times. Okay, this is times 6. From 0.01 to 0.06. What happened to my rate? My rate went from 5.4 to 32.3, which is times 6. Direct effect. What I did to the concentration directly affected the rate. Alright, so now that I have my orders, I can come up with a rate law for this. And I'm going to use this. And I'm going to write the differential rate law. So for this reaction, the reaction of ammonium and nitrate to yield nitrogen gas and water to water, we can say the rate is equal to the reaction constant, little k, times ammonium raised to the 1 and nitrite also raised to the 1. And we've just come up with our differential rate law using what we call table logic. So, what does all this mean? Well, first, the rate is affected by the concentration of ammonium. Second, we also found that the rate is affected by the concentration of the nitrite. So, if this is affecting the rate and this is affecting the rate, the two of them together affect the rate. Well, how do they affect the rate? That's where K comes into play. K helps determine exactly what the calculation for your rate is. Alright, so the rate is equal to K times NH4 raised to the 1, ammonium raised to the 1, and nitrite raised to the 1. Okay, technically there really should be some 1s here. So let's just put some 1s in. Why? Because we've already determined how this reaction is affecting the rate when you change the concentrations. Alright, and there's my rate law. Rate is equal to little k, which is the rate constant, times the concentration of ammonium, raised to the 1, times the concentration of nitrite, raised to the 1. That gives me my rate law. From here, we can do a lot of math. If we plug in some numbers from our data table, like the rate for a trial and the concentrations in those two trials, then we can calculate K. And K is going to be constant for every trial, and in that same kind of reaction, K is going to always remain the same. And you'll see that when you do a little bit of math dealing with differential rates. Alright, therefore, how do we calculate K? Well, if rate is equal to K times the reactant raised to its order, reactant 2 raised to its order, blah, 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 we can rearrange this equation and get little k by itself. And little k is equal to rate divided by the concentration of the reactants raised to its order, concentration of reactant 2 raised to its order. All you do then is plug data in from your table. Now here's where things get tricky. The units of little k depend on the overall order of the reaction. How do you find your units? You plug in your units. And you'll start to see units will start canceling out, and you'll end up with different units, because the units are dependent on the order. Alright, how do we get what's called the overall order of a reaction? Well, that's super easy. The overall order is the sum of the orders of the individual reactants. So, if rate is equal to K times the concentration reactant raised to the M, concentration reactant 2 raised to the N, what's the overall order? It's M plus N plus any others that might have an order. That's what overall order is. Alright, so let's do this problem together. See how you guys do. Alright, we have a reaction, A plus B yields C. And it's measured using several different starting concentrations, and they gave us a whole bunch of data. They give us the concentration of A's in different trials, the concentration of B's in different trials, and their initial rates in these different trials. Alright, so let's figure out what is the order of my reactants and come up with a rate law. So, using table logic, we want to find trials where A stays the same and B changes. Alright, so let's look at trial 1 and 2. Alright, what happened in trial 1 and 2? A stays the same, it's constant. Right? What happened for B? Well, B, it doubled. Okay? Because it went from 0.1 to 0.2. So we doubled the concentration. Alright, what happened to the rate? Well, if you look over here, what happened to the rate? It started at 4, and when I changed this concentration, the rate was still 4 times 10 to the negative 5. Alright, so the rate stayed the same. So, did changing the concentration have an effect on the rate? Alright, and in this case, it did not. Alright, so what can we say about the order of B? B, we're going to give it an order of 0. Why 0? Well, changing the concentration had no effect on the rate. Alright, and so that's what you're talking about when you're talking about changing the rate. Alright, so now let's find two trials where B stays the same and A changes. Alright, and that would happen in trial 1 and 3. So in trial 1 and 3, B is the same. It's 0.1 in both of them. Alright, and what happened to A? Well, A doubled. Alright, and then we look at this in trial 1 to trial 3. What happened to my rate? Well, my rate went up by 4. Alright, so what's the relationship between 2 and 4? Well, it's an exponential relationship. When the concentration is doubled, then the rate goes up exponentially, 2 to the 2. Alright? And so what can we say about the order of A? Well, A is the second order. Alright? Because it went from 4 to 16. So now that I know the orders of both of my reactants, I can write the rate law. So I would say rate is equal to little k times the concentration of A squared times the concentration of B to the 0. Alright, what's our overall order of this reaction? Well, overall, it's a 0 plus 2, which makes this a 2. Alright? From here, we can go to a lot of places. Alright? We can calculate K. How would we calculate K? Alright? Rearrange the equation and find K. So what's K? Let me go down a little. Alright? K is equal to rate over the concentration of A to the 2 times the concentration of B to the 0. Alright? Let's plug some numbers in and calculate a K. It doesn't matter which one we use. We could use the data from trial 1 or the data from trial 2 or the data from trial 3. It doesn't matter. They're all going to end up calculating the same K. So, let's just go ahead and use 1. Why? Because it's the first. And why not? And my numbers are easy enough numbers that I could do this without a calculator. So what's my rate? It's 4 times 10 to the negative 5. And I'm going to go ahead and put some units on here. Molar per second. Alright. And then I'm going to divide it by the concentration of A. So what's A? It's 0.1 molar, and that is squared, because A was a second order, and then it is 0.1 to the 0. Alright, so we have 4 times 10 to the negative 5 divided by 0.1 molar squared times 0.1 molar raised to the 0. Well, what's anything raised to the 0? That would be a 1. So this is going to go away. Alright? So then we're going to have 4 times 10 to the 5, or 10 to the negative 5, and that's going to be molars per second. And that's going to be divided by 10 to the negative 1 squared. Alright, I changed that to 10 to the negative 1, so I could easily do the math here. Alright, so I have 4 times 10 to the negative 5 divided by 10 to the negative 1 squared. What's 10 to the negative 1 squared? Well, it's 10 to the negative 2. Alright, so that helps these two things cancel out. And so for a number, for a k, I get 4 times 10 to the negative 3. And if you don't believe me, plug in your calculator, you'll get it. Alright, my units. Let's deal with our units. I have molars per second divided by molar squared. Alright, so what does that end up being? It ends up being 1 over molar seconds. Alright, because molar divided by molar squared gives you a molar in the denominator. And we still have a second in the denominator, so we end up with molar seconds. And that's how you get the units for K. You are always going to have to calculate the units for K, because they're different, because it depends on the order of your reactants. Alright, one more example. Make sure you guys are doing okay on this. Alright, here we go. It says the following data is measured for a reaction of nitric acid and hydrogen. So there's my balanced chemical equation. And they give me some data. There's the concentration of nitrogen oxide, nitric oxide. Here's the concentration of hydrogen. And here are the rates. So, step 1, we're going to find a trial where nitric oxide stays the same and hydrogen is changed. So we can use this first trial. Alright, so in trial 1 and 2. Alright, what happened to my NO? Stayed the same. Alright, what happened to my hydrogen concentration? It doubled. Alright, and then finally, what happened to my rate? Well, my rate went from 1.23 times 10 to the negative 3 to 2.46 times 10 to the negative 3. And so what is that? That is a double. So, the question is this a no effect, a direct effect, or an exponential effect? And because this is doubled, and this is also doubled, that is a direct effect, which tells me that hydrogen is a first-order reactant. Alright, now we're going to go to trial 1 and 3. Why? Because in trial 1 and 3, hydrogen stayed the same. Alright, what happened to nitric oxide? Well, it went from 0.1 to 0.2, so what did we do? We doubled it. Alright, now let's look at our rate. Remember, we're comparing 1 to 3. So what's the relationship between this rate and this rate? It's times 4. So is this a no effect on the rate, a direct effect on the rate, or an exponential effect on the rate? It goes from 2 to 4, and 2 and 4 have an exponential relationship, so that tells me that NO is a second order reactant because it has an exponential effect on the rate. So now that I know the orders of my reactants, I can write my rate law. Rate is equal to K, little k, times NO to the 2 and H2 to the 1. What's my overall order of this reaction? Well, the overall order is 2 plus 1, which gives me a 3. So if they ask me about overall order reaction, I could do it. Alright, so let's look at some of the other questions associated with this problem. We already know our rate law. Alright, so next question is calculate the rate constant. So what am I trying to calculate? I need to find K. So I'm going to rearrange my equation for K. So I'm going to say K is equal to rate divided by NO squared and H2 to the 1. Now we just plug in some numbers. It doesn't matter which trial you pick any of them, but just plug in the numbers. I usually pick the first one. Why? Because it's first. And my numbers look somewhat easy. So I'm going to plug in my numbers. 1.23 times 10 to the negative 3 molar per second divided by, and in the first one I have 0.1 squared times 0.1 to the 1. Alright, let's do a little math. 1.23 times 10 to the negative 5 molar per second divided by 0.1 squared is 10 to the negative 2 times 0.1, or 10 to the negative 1, gives me 10 to the negative 3 molar cubed. Okay, let's look at our math. We have a 10 to the negative 3 on the top and a 10 to the negative 3 on the bottom. So guess what they do? They cancel out. And so my K is 1.23. What are my units for K? I have molar per second divided by molar cubed. So that ends up being 1 over molar squared seconds. Now, see how my unit for K was different? Well, it was different in this problem because my orders were different. So you always have to calculate the unit for K. And then the last question says, okay, well now let's calculate what the rate would be, question mark, if the concentration of nitrogen our nitric oxide was 0.05, and the concentration of the hydrogen was 0.150. Well, we just calculated K, and we're going to use that number right there and plug it into our rate law. So we know rate is equal to K, and this point K is 1.23 molars squared seconds times the concentration of the nitric oxide, which in this case it's going to be 0.05 squared, because that's the order, times 0.15 to the 1. And now you just do a little bit of math. And when you do the math, you get 4.6125. Sorry about my 6. Times 10 to the negative 4. Okay, that's my rate. Now let's look what happens with my units. Remember, this is molar, and this is molar. So I end up with molar cubed over molar seconds. And so what does that become? It becomes molar per second. Does that match what I got for my rate? Yeah, that's a rate unit. Molar per second. So I'm going to give you guys some practice problems from the book. The assignment is on the board, and I want you guys to work through these practice problems for your homework and see how you guys can do with table logic. Honestly, table logic, you just need to practice. If you don't practice table logic, then you're going to have a hard time with the differential rate law. So start with the homework tonight and work with those problems, and we will go over them on Friday. And then the last thing I want you guys to make sure you do is we're going to be doing our silver ornament lab on Friday. You need to read the protocol, which is online, and make sure you understand what you're doing. There's no pre-lab associated with the protocol. I just want you to make sure that you understand what you're going to be doing in the lab, because we need to get in there and get done very quickly in our split block on Friday. Alright, so I hope this helps. If you didn't understand some of it, work through your practice problems for your homework, and you can watch this video again. I'm going to post it online so you guys can watch it. So, thanks, and I hope you guys have a good rest of the day. Bye.